Okay. So in the last class, we have already shown that conservation of linear momentum is due to the homogeneity of space. So if a system is displaced in space, there is nothing happens to the system. No change for the system, and you get the same results for any experiment. That means space is homogeneous, and that property you can connect with the, that is the reason, fundamental reason for conservation of linear momentum. Next is again due to the homogeneity of space, sorry, time, we are displacing an event, a system in time. Means you are doing an experiment today or tomorrow or you did yesterday. Whatever be the case, you get the same result. So that homogeneity in time leads to the conservation of energy. Okay. So this is the idea. We have to find the operator, unitary operator, which does this time translation. So unitary operator is capable of doing any kind of transformation. So find such an operator which is generated by another operator. Unitary operator is generated by another operator, and since unitary operator commutes with the Hamiltonian, that corresponding operator will commute with the Hamiltonian, and that can be anything which commutes with the Hamiltonian can be taken as the constant of motion. So any quantity which commutes with the Hamiltonian is a constant of motion. So now you consider an infinitesimal, very small displacement in time, delta t. So we are displacing a system by a small time delta t. So the nothing happens to the system. So I mean that means the wave function is same before and after. So you can equate the wave functions before displacement in time and after displacement in time. Okay. So let the wave function after displacement is psi dash. Okay. And before displacement is psi. Or you can take the reverse also, no problem if you take the reverse also. So psi dash of xt equal to psi of, there is no change for x is same. You are not displacing in space, you are keeping the experiment in same laboratory, same position, no change for position, but you are repeating the experiment after some time. So t becomes t plus delta t. So wave function should be same at both the time instance. That is the idea. Nothing happens to the system since time is homogeneous. So the wave function before and after displacing the system in time is same. So that you can here you can take minus t minus delta t plus delta t, that means before or after. So that is technically both are correct. You can take whatever way. You can take t minus delta t or t plus delta t, no problem. So we just before some time and after some time, that is the meaning. So this expression psi of x t plus delta t you can expand using the Taylor series. So Taylor series is a very powerful tool where we can use at many places. So that can be written as psi of xt plus a small interval delta t into slope of the wave function dou psi by dou t. This is the Taylor series expansion. Okay, I think this is clear. Any function can be expanded around a point. So we are expanding this function around the point t, time, in time. So psi of xt plus a small variation in psi, that is dou psi by dou t into delta t. Okay. So this can be written as psi of xt plus, now you put a I by h cross, an additional I by h cross, then you cancel it with the minus ih cross. So minus I square will come, that is 1. The h cross also cancels, that is 1. So this can be written as psi of xt. This is same. This one you can write it as I by h cross delta t minus ih cross dou psi by dou t into psi of xt. This psi we have written as psi of xt. Now you can combine these two. Take psi of xt outside. So psi of xt, you put it on the right side. So here it is 1. Then I into delta t into uh, this ih cross dou by dou t, or ih cross dou psi by dou t is nothing but h psi according to Schrodinger equation. According to Schrodinger's equation, time dependent Schrodinger equation, ih cross dou psi by dou t is h psi. E psi equal to h psi. This is E, actually E, energy operator. E psi equal to h psi. So we replace this ih cross dou by dou t by minus other by capital H, Hamiltonian operator. Okay, according to the Schrodinger's equation. So psi of t is outside. This you replaced by capital H. Now h cross we have taken here minus h by small h cross, minus capital H by h cross. That you have taken as the, that you can take it as the generator of the time translation. So this format we have already discussed earlier. This you can write it as e to the power of minus I by h cross h into delta t into psi of xt. So this this is the generator of unitary operator. So finally psi dash equal to e to the power of this minus this quantity into psi. So that e to the power of minus quantity is the unitary operator. So we identified this operator, unitary operator, which is capable of doing the time translation. So this is the operator, unitary operator. Okay, and H is, we know H is Hermitian. So this is a Hermitian operator which generates unitary operator U, which is capable of doing time translation. So this minus h by h cross, this quantity may be defined as the generator of time translation. I think the idea is clear. The same thing we have done earlier in the case of linear momentum. So this is there we did the space translation. Here we are doing time translation. Okay, so psi dash you can write it as psi dash xt, you can write it as e to the power of minus I delta t capital H by h cross psi of xt. So this is the unitary operator. If you take u dagger, this will be 1. So this is unitary, which can do the infinitesimal delta t time translation of the system. Okay, thus the unitary operator, this is the unitary operator corresponding to the infinitesimal displacement in time delta t is this one. You can represent it by uh, because h is the generator of u. So write it as u suffix h. H generates u, or h by h cross is the generator. So uh, which is doing delta t translation. So delta t equal to e to the power of minus I by h cross H delta T, which you can write it as 1 minus, as earlier, as before, we can write it as 1 minus x. E to the power of minus x, you can write it as 1 minus x. 1 minus I delta T h by h cross plus etc. That you can neglect, higher terms. Because this is very small, delta T is very small, you can neglect the higher terms. So here h is the Hamiltonian, which is independent of time. Time independent Hamiltonian. That means time dependence of Hamiltonian comes through the potential. Potential is time independent. So h is also time independent. So h generates u. Okay, so you can do the time translation of the system. You operate with u, system will be evolved in time. Okay. So the invariance of Hamiltonian under time translation, we know that nothing happens to the system. If you do the time translation, no change for the system, means no change for the Hamiltonian. Hamiltonian becomes invariant before and after time translation. So invariance of the Hamiltonian under time translation requires that h dash before or after, you can take h prime, you can take after after time translation, h dash equal to u h u dagger. This is how operators are transformed. That should be equal to h. If you do h dash and h should be same, then only time is homogeneous. No change for the system under time translation. If you do experiment today or tomorrow at the same position, you should get the same result. No change for the results. Nothing happens to the system. So h dash and h should be same. So means that we say h is invariant. So this equation you can multiply with the u on the right side. So u here, u here. So u dagger u is 1. So this becomes uh equal to hu. Operate with a u on the right side. That means uh equal to hu, or that is h commutes with the u. This you can write it as commutation hu equal to 0. So this you can write it as hu equal to 0. Commutation of unitary operator with h is 0. So similarly, if u commutes with h, the generator also commutes with h. Here generator was h by h, and its eigenvalue of h is E, energy E. Eigenvalue of h is E. Operator is h, corresponding eigenvalue is E. When you consider the time independent potential or time independent Hamiltonian, you can write h psi equal to E psi, where E is the scalar eigenvalue. Okay, so if h commutes with u, we can claim that h commutes with the generator of u also, which is h operator, and its eigenvalue E, energy E. So this means h commutes with E, or anything commutes with h is a constant. So here E is a constant. The energy becomes conserved. So u or uh commutes with h, since h is independent of time. If h depends on time, case is different. This is conservation of energy is not true. If h is independent of time, conservation of energy is true. So the time independence of h means that the total energy of the system is conserved. H is independent of time means total energy is conserved. That is the conservation of energy, principle of conservation of energy. So the system is, total energy of the system is conserved if the system is invariant under translation in time. So that is due to the homogeneity in time. You translate in time, system remains invariant, Hamiltonian remains invariant, so energy will be conserved. So if H depends on time, the conservation of energy will not be valid. So the minimum condition is that H should be independent of time. H dependence of H on time comes through the potential. So if potential is independent of time, H is independent of time, so the energy will be conserved. So finally you can write energy of system is conserved when, if the system is invariant, if the system is invariant under translation in time. Translation in time, and the reverse also is true, and vice versa. So this is the result obtained from the homogeneity of time. Okay, so you can always connect this with uncertainty also, energy and time, position and momentum. See, there is a that is why they are actually connected. Time is connected with energy uncertainty, X is connected with the space is connected with the momentum uncertainty. Okay, so the next topic is conservation of angular momentum due to the isotropy of space. So do you do the rotation in space? So you do perform the rotation in space. You can see that since space is isotropic, that leads to the conservation of angular momentum. Let me put L. Conservation of angular momentum. Okay. Is the previous idea clear? Conservation of energy clear? Somebody may respond.
Yes, sir.
Okay.
Yes, sir.
Now we will discuss rotation in space. You are doing experiment in one direction, in east-west direction or north-south direction or some other direction. Result is same. Space is isotropic. So you consider rotation that we have already discussed. We can perform that in two ways, either active rotation or passive rotation. So consider two frames O and O dash. O, X, Y, Z, one frame, S frame, let it be S frame, and O dash frame, O dash X, Y, Z, which is the S dash frame. So consider two frames for doing this passive rotation. If it is active rotation, we have only X, Y, Z. So frame is fixed, X, Y, and Z. You can take Z here also. So you are rotating means you have a vector here, then you are rotated it to through an angle delta theta. Okay. So initially the coordinate is x, y, z. Finally the coordinate is x dash, y dash, z dash. So here you are rotating the vector, keeping the coordinates fixed. The another case is again the same thing, x, y, and z. So you have the vector here. Now, so you have to, sorry, you have to consider this one initially. This is the initial vector. Okay. Then you are rotating the coordinates. Okay. So that x dash, y dash, and z dash. So that you have rotated through an angle d theta, delta theta. So the vector, new vector is, you have rotated it anti-clockwise. Coordinate system you rotated anti-clockwise, so that initially it was here P point P, now it becomes here. So again this angle is also delta theta. So in two ways you can rotate. So in whatever way we have already learned that, so the new coordinates and old coordinates you can connect using the an orthogonal matrix, which is, we have already learned this, x dash y dash equal to cos theta minus sin theta or plus sin theta minus sin theta cos theta, then acting on xy. So this is the mathematical way of rotating about the z axis. There is no change along the z axis, it is rotating along the xy plane. Okay. So you can write this transformation equations as x dash equal to x cos theta. You multiply this row and column, x cos theta plus y sin theta. Okay. And y dash equal to, sorry, we have to uh, consider the infinitesimal rotation. So you have to put the delta theta here. Now y dash equal to, so this angle also you can put it as delta theta. So y dash equal to minus x sine delta theta, then plus y cos delta theta. And there is no change for z, so z dash equal to z, because we are rotating about the z axis fixed, rotation is along the xy plane, so no change for the z axis. These are all we have discussed earlier, so I think we don't have to spend too much time. This is known to you. Uh, this is a particular kind of group, special orthogonal group. Okay. Now, when theta is very small, we know what is the condition. When theta is very small, when delta theta tends to 0, what is cos delta theta and sin delta theta? When theta is very small, cos delta theta is 1 and sin delta theta is delta theta. Okay, I think that is clear, known to you. So we can change that equation. This was our equation. So let us change that equation. X dash becomes x cos delta theta. That is 1. Okay. Plus y sin delta theta. So that is delta theta. Okay. Now y prime. Y prime or y dash is minus x sin delta theta. So minus x delta theta plus y. Okay. I think that is clear. Z dash equal to Z. So apply a limiting condition, delta theta equal to very small, infinitesimal. So you can approximate that equations like this: x dash equal to x plus y delta theta, y dash equal to minus x delta theta plus y, and z dash equal to z. Okay. Now these are nothing about this kind of conservation. This is just a rotation. How rotations can be manipulated mathematically using this matrix, special unitary matrix. You can perform the rotation. Okay. Now we know that the wave function before and after rotation is same. So psi at a point P has definite value independent of space coordinates. Okay, that means we are rotating the system, nothing happens to the wave function. So you can write psi dash r dash equal to psi of r. Wave function is same, no change for the system. Okay, so you can write this one as psi dash, instead of r dash you can write the 3 coordinates x dash, y dash and z dash. That is x plus y delta theta minus x delta theta plus y, then z equal to. So we these 3 coordinates we have written for x dash, y dash and z dash, and that should be equal to psi of x, y, z. Okay. Now for convenience you take this one as, for convenience let us take uh, x plus y delta theta as uh, x, and y minus x delta theta as y, and z dash equal to z. Okay, or is z equal to z dash, z equal to z. So you can expand this psi dash x, y, z as psi of uh, x minus, so let me write this one has capital X, this is capital Y and capital Z. Okay, so psi dash uh, X psi dash XYZ, you can write it as psi of, just to change X is X, you can write it as this small x, you can write it as capital X minus Y delta theta. Okay, so capital X minus Y delta theta. So this is small x. So this is capital X minus Y delta theta, and capital small y, you can write it as capital Y plus X delta theta, and Z is not change, Z is same. Okay, now you can expand this using the Taylor series. That is, this you can write it as psi of X, Y, Z, then plus uh, here two X and Y are varying, so this two you have to write, so delta theta into this is minus y dou psi by dou x. Okay, minus y dou psi by dou x. This one plus from this one you will get x into delta theta is here, dou psi by dou y, and z term goes. So this is the Taylor plus etc. This is the Taylor series expansion of this equation around the point x, y, z. So this you can write it as psi of x, y, z plus, now you put a I by h cross here into delta theta. So this one you have to cancel with minus I h cross inside the bracket. Okay, so that is x into, I am writing first, I am writing this one, x into minus I h cross dou by dou y. Now this one, first one, minus y into minus I h cross dou by dou x. There into psi. Okay. So just add I by h cross, cancel it with minus I h cross. So this can be, we know that LZ is, what is LZ operator? Minus I h cross x dou by dou y minus y dou by dou x. Same thing is here, LZ operator. We know LZ operator, angle Z component of the angular momentum. So that is this one. So this is the same operator. So you can write it as psi dash xyz equal to, so this equation you can write it as psi dash xyz equal to psi of xyz This notation you have to check. Then this can be written as I delta theta I by h cross delta theta, oh sorry, this one plus I by h cross delta theta into Lez psi of Lez into psi. So now you can take the psi on the RHS. So this will be 1 plus I by h cross or Lez by h cross into delta theta Lez into psi. So we found the unitary operator, okay, which does the rotation. So who is the generator? Generator is Lez by h cross. Time is over. I will start another session.